Okay, so thanks for being here. And my talk is going to be, to some extent, very similar in spirit to the one by the previous speaker, James. Of course, I have a different perspective, so probably I will emphasize different points. And the main difference will be that I will not attempt or even suggest an assessment of different approaches or even different programs. And the reason for that is that, in fact, one of the main goals will be to show how complex is that assessment. And so that, of course, each one of us does it in the everyday life and in choosing what to work on, and we have our preferences, but it stays there. I wouldn't raise any such assessment that I could do or as something more objective than that. I mean, the facts are objective about the different status. What to make of that set of facts is a different story. So you have seen already, and I'm going to emphasize it again with a different picture, that there are a number of approaches to quantum gravity. And the picture is not representative of the size of the communities, it's not representative exactly what I think about different approaches. And I didn't even try to group them in any specific manner. I just made a list and I pointed out connections that I'm aware of within some of them. And then if you're trying to portray the quantum gravity landscape, it's not just about different formalisms. There are a number of areas of quantum gravity research which are sort of formalism independent, but they are interesting and growing and fruitful areas of research which can say a lot about quantum gravity, but they're not tailored to any specific approach or formalism. The point that I want to get across just from this picture is nothing quantitative, but it's just that there is indeed a great variety and there are many mutual relations. And what I'm going to expand on later is the fact that there are many shared issues and mostly the same goals overall. The other point is that all approaches are incomplete in different ways, depending on which one you focus on. There are missing parts, and which parts are missing also depend, to a large extent, in fact, as well as the achievements, on the strategy and the perspective that has been adopted in setting up a given program. So that also has to be taken into account, assessing the status of each of them. The other point is that that's the science, the bird's eye view on the science. Then there is the fact that there is a huge community, well, huge. In theoretical physics standards, it's a small community, even if you put together all quantum gravity sub-communities, but it's a rich and diverse one. And the relations can be difficult across different sub-communities. The other point at this level is that, as it has been emphasized earlier, the different sub-communities are not of comparable size. I mean, they can be of very different size. But I want to say that just like the problem of quantum gravity is rich and complex, even the counting of how many people work on the given quantum gravity approach is a little bit ambiguous, because the boundaries between different formats are ambiguous. And in fact, the research directions, what actually people work on within a given formalism is a bit ambiguous, can be very diverse itself. I mean, not everybody you would count as in the, I don't know, deep quantum gravity community actually works on problems which have to do with quantum gravity. Many may branch off to more mathematical issues that are motivated maybe by quantum gravity, but so when you count how big are the communities, are you counting those that actively work on solving some specific quantum gravity issue within the formalism, or you have another way of counting? The other thing is that there are different historical rules, and that influences the size of the communities, it influences the perspective, it influences the type of tools they use, and the criteria for for tackling one specific problem rather than another one. And that's also why communication across formalism and across subcommunities can be difficult. There are different languages and different definitions of what the quantum gravity problem actually is. So there are a number of factors affecting the existence, the development, and the communication across different subcommunities. And then there is some more scientific aspects, and this is what I'm going to focus on. Not because I want to forget about the others, because they're relevant, but because you have to choose what to focus on. So I have two goals with this presentation. I want you to appreciate why such diversity is there. Second, I want to consider the issue of non-empirical theory assessment in light of the nature of the quantum gravity problem and the status of the quantum gravity landscape. So not in abstract terms, but in this specific context, given what I just said about the problem, what I will say about the problem and the community. There are two claims that I'm going to make. One is that not only this diversity is a fact, but it can be beneficial. In fact, it should be beneficial. And so we can try to make use of it to make progress. In particular, in the context of non-empirical theory assessment. So first point, there's no single quantum gravity problem. There are actually many problems. There are a number of motivations, conceptual, physical, and so on. And they refer to different sub-problems within the bigger quantum gravity issue. The conceptual level is more or less clear. I know we want to merge the setups of general relativity, the main lessons from there, with the main lessons from quantum mechanics, quantum field theory. And we know that we need something more than just putting them together, pretending gravity can be classical and matter could be quantum. There's no proof of that, but that's the consensus, and there are a lot of good arguments. There are a number of physical motivations. Again, why am I going through the various motivations? Not just to introduce the problem, but which motivation you weight more counts for how you evaluate different programs, different research programs, and simply what you decide to work on. So there is the issue of singularities in black holes and the cosmological one. There is the issue of what happens to matter fields at very high energies, where you expect gravity to be also relevant. There are a number of other physical issues. We expect that cosmological scenarios, existing cosmological paradigms, require quantum gravity to complete them. And quantum gravity effects may be directly impactful in cosmological dynamics and early cosmology physics. And in fact, even late cosmology, the issue of dark energy, if you decide is related to quantum gravity, or could be related to quantum gravity, and that's for a number of reasons quite reasonable, well, it's not going to be just high energy effect. And then there are the issues related to black hole, and I just mentioned two. One is the very fact that black holes seem to have thermodynamic properties, and given that black holes are just regions of space, and or particular configurations of what we would say is the gravitational field, if they have thermodynamic properties, maybe you suspect that space itself, space-time itself, has thermodynamic properties. And that suggests that it has some underlying microstructure. There's something more to be said on top of, oh, I have a black hole, which is a particular geometry. And the second is the infamous information loss. The fact that black holes evaporate leads to the question of what happens to the information which is inside them towards the end of the evaporation process, which is closely tied also to the issue of the singularity at the center of black holes. And that's where quantum gravity, something that quantum gravity is expected or hoped to solve. Now, how one approaches these physical issues will depend on the perspective on quantum gravity. It's not even if after I buy the statement that quantum gravity is needed, how I approach these issues depends on what perspective I take on quantum gravity. And then, of course, it depends on the specific formalism. But it works also in the other way around. How I assess a given quantum gravity formalism depends on which conceptual and physical motivation I value the most, which ones I take as this is a necessary condition to evaluate positively a given program. These ones are welcome but secondary. We are here with the excuse of lack of experiments. But one thing that I will not expand too much upon, but it's a fact, I think, is that it is simply not true that quantum gravity is expected to be for a long time away from any experimental test. There exists a large area of research devoted to quantum gravity phenomenology. And there are many, many examples of effects that could be traced back to quantum gravity properties, which are testable or will be testable in the near future. Not the place to give a survey about that, but it's a fact. There are a number of observable or potentially observable effects. And so I resonate with what Irene was saying this morning. It's simply not true that, the idea, simply not true that quantum gravity is at such high energies that it's almost impossible to test. The problem is actually with the theory. It's not so much with the experiments. Our experimentalist friends are much cleverer than we normally make them. With all due respect, they're even better, even more clever than what we pretend. The point is that most of the quantum gravity phenomenology at the moment, due to lack of a solid theory, are constructed, are carried out in terms of purpose-built phenomenological models or scenarios that incorporate some hypothetical or suggestion from quantum gravity formalism. Or they are simple models for specific extreme physical situations, again, inspired by specific approaches. Or there are some ideas that are, again, implemented in toy models, but we don't really know if they are realized in some quantum gravity formalism. One example being, I don't know, violations of space-time symmetry. Whatever I think about that is not that we know that a given quantum gravity formalism violates local Lorentz invariance, or that it doesn't, in fact, in many cases. But we say, okay, if quantum gravity has some violation of Lorentz invariance due to some minimal length that has to be present in the theory, this would be the phenomenological consequences. And some effects are already ruled out. So it's more than, you could hypothetically do experiments to check this possibility. In doing phenomenology, a lot is based on effective field theory reasoning and intuition, which is reasonable because it's the best tool we have to do physics. On the other hand, as I'll try to emphasize, if there is something we know about quantum gravity, is that it's going to replace almost all of the ingredients that go into effective field theory. So we do, of course, what is reasonable to do. You start from what you know, you try to push it. But we also have to be careful in maintaining that the only effects that are reasonable to find are those modeled by effective field theory. Okay, then an important ingredient when one tries to do phenomenology is some degree of model independence, and which is nice. You don't want to do phenomenology in a way that is necessarily tied to one specific microscopic theory with one specific choice for solving its ambiguities. But the problem is that most of the ingredients that allow us to do phenomenology in a model-independent manner, so in a more reliable manner, are in fact difficult in the quantum gravity context. And once more, the main reason for that is a lack of strong enough contact with the microscopic fundamental theories. So the consequence of all of this is that there is a field of quantum gravity phenomenology, but we have no real test of fundamental theories directly, no real predictions from the fundamental theories. We have a number of indications. We're making progress. So you have seen the talk about the swampland. There are other examples. So we're certainly making progress, but the reason why, well, I guess we are here today is that we cannot really claim this theory has been tested or is gives this particular prediction and this has been falsified. And more generally, it's certainly true for the field of quantum gravity as a whole that it is not an area of research which is data-driven. We are not, as theorists, trying to catch up with experiments and observations and try to show that my best favorite quantum gravity model or formalism fits so well all these data that are so puzzling. We are not in this type of physics. So the consequence is that there is inevitably a very large room for non-empirical theory assessment. So there's no problem with that. It's a fact, and it's something we just have to investigate to be more careful about. So what about some directions in the landscape of quantum gravity approaches? So the one reason why there are so many routes is that the most conservative, simplest, least conceptually challenging route to constructing a theory of quantum gravity has been shown to fail. Because if that had worked, we would have said, okay, maybe we need to we have to improve. There is much more to be said, but okay, we have a theory. Now we complete it. No extra ingredients, no new methods, standard quantization of a field, in this case, the gravitational field around a given space-time, you quantize. We get the notion of gravitons and so on, but we know is not the definition of the theory. So we know that the vacuum of quantum gravity is not a Fock vacuum for gravitons or similar excitations over cosmic space. We know that the UV theory is not going to be some free theory. And we know that the gravitons themselves are not the fundamental degrees of freedom. We also know, however, that this type of approximation has to be recovered. So we do learn a lot of things from this story. So how can you react to that? It has been mentioned already. You can say, okay, we know we cannot quantize the gravitational field in terms of its perturbations around a given configuration. We have to quantize non-perturbatively. And there are a number of methods to do that. Some approaches try to do exactly that. Or you can say the failure of perturbation theory plus the hypothesis or the conviction that whatever is the theory of quantum gravity should be well defined perturbatively in the same sense in which you expand around a given solution, but that perturbative expansion should be well defined. Well, this result tells me that in perturbation theory, to make sense of quantum gravity, I need new degrees of freedom or new symmetries. And that's, for example, what the string theory and to some extent supergravity try to do. The point here is that even if you take this route, everybody agrees that you will need a non-perturbative completion. So it's not, these two things are not really alternatives. You may say, I want to insist that my theory of quantum gravity needs to have a well-defined perturbative expansion around a given background. And then, under this assumption or conviction, then I need to introduce extra symmetry or degrees of freedom. Then I will still need to face the type of problems that I have in the first approach. In that approach will be confined just to the gravitational field and standard matter fields in terms of non-perturbative quantization, but I have the same issues with the extra degrees of freedom and new symmetries there. Of course, the new symmetries and new degrees of freedom may well help in addressing the type of issues we have here. In fact, there is a third option, which is that you do have to change degrees of freedom, but not looking at what the perturbative expansion tells you. You should look for new degrees of freedom that really replace the whole setup of a given spacetime plus perturbation. So it's spacetime itself that has to come out as a collective excitation of a different type of degrees of freedom that then by definition cannot be defined in terms of a given space-time geometry in this sense, and they're not the gravitational field itself. So in this sense, they're not spatio-temporal themselves. From this point of view, then space-time is some sort of a quantum many-body system with individual, atoms or molecules or whatever. They are not themselves defined in terms of space-time or geometric properties. And this is also true from slightly different perspectives in a number of approaches, in particular when you take discrete type of structures as fundamental. Why we would go to embrace this type of perspectives? Well, there are motivations from a number of semi-classical results. And there is also the fact that some of the approaches that start from the previous points of view suggest and give you hints that maybe the very notion of space-time they will rely on is in fact some emergent notion. And okay, these are hints summarized from approaches that were initially motivated and are motivated by non-emergent space-time point of view that still suggests an emergent space-time picture. Okay, so this is some sort of how people may start, what are the motivations and so on. But what do we expect? What should be required from a theory of quantum gravity? Well, this is a list of ingredients, and I'm going now to say more about some of them, which I would claim everybody agrees. So these are features that whatever is your favorite formalism, at some point you should show to have achieved. You have to tell me what are your candidate fundamental degrees of freedom that make up space-time, matter fields, and so on. What are the basic entities in your formula, in your theory? You have to control the quantum aspects of space-time and geometry, and I will say something more about that. If you want to claim that you have a theory of quantum gravity, well, typical features of any quantum system should be there and under control for gravity, for space-time itself and geometry. You need to be able to do local physics, because we do local physics. And the problem in quantum gravity, as I'm going to discuss in a second, is to identify observables with a local space-time interpretation at the quantum level. But in fact, I would say that there is some issue there already, the classical one. Then you have to, once you're in this framework, you have to give me a proper definition of the quantum dynamics of your degrees of freedom. And then you can show a semi-classical approximation is obtained in some regime of the theory. Now, this is this simple way of phrasing it assumes that my fundamental degrees of freedom have somehow already the interpretation of quantum gravitational field or quantum matter field. If those are themselves emergent, there is a further issue, which is what could be basically called the continuum approximation issue. And more physically is that you have to control the collective dynamics of whatever are your non-space-time based degrees of freedom. And show how the very notion of space-time in geometry and gravity emerges. Once you have a good control over the dynamics and the semi-classical limit, and in case the continuum limit or continuum approximation, then you have to compute observables, extract testable predictions, and you do phenomenology. Maybe connecting to existing toy models or phenomenological models already in use in the area of quantum gravity phenomenology. The other thing that everybody agrees, but I said it already, is that the perturbative framework in which you have some GR-like solution with quantum field theory for excitations on top of the solution should be recovered in the language of effective field theory. I just want to emphasize that the two ingredients, background space-time geometry and the quantum field theory on top, should both be recovered from the full theory. So the background space-time itself is something that you should recover. It's a result. It's something to derive. So these are many tasks, and well, some of them are easier in a non-perturbative approach. Others are more challenging in a non-perturbative approach, and vice versa for perturbative ones. If you start in terms of continuum fields or their generalization, then some tasks are easier and some others are much more difficult. So let me mention just some of them, let me give a few more details about some of these issues. So we say we need to control quantum properties of the gravitational field, assuming that it has been already obtained maybe by some post-graining of more fundamental degrees of freedom. So whatever is your approach, you should have some notion of a quantum theory of the gravitational field. Maybe it's an approximate description itself, but you have to have it under control, which means you have to have some Hilbert space of the gravitational degrees of freedom of the gravitational field. You have to have observables acting in such states. You have to be able to compute spectra. You have to be able to compute superpositions of spacetimes, and so on. At the quantum level, you need to have some constraint, some operator, some equation, or some path integral expression for the quantum dynamics for such states. A key point is that, again, regardless of the specific approach, if you get to the stage in which you have a notion of gravitational field, but you're still in the quantum regime, you're not doing semi-classical gravity, you're going to have no external preferred notion of time or space. So your notion of dynamics is some constraint equation or some path integral not labeled by any time direction in general. Then there are special cases, of course, within the theory. And the other thing that you have to be able to control conceptually first and then mathematically is the idea that space, time, and geometry fluctuate and evolve probabilistically. This is just logical consequence of putting together the statement that you have a quantum theory and the statement that it's a quantum theory of the gravitational field and matter. It means that all geometric quantities, everything, the area of the surface, the distance between me and the bottom of the room, and so on, all these geometric quantities are subject to superposition, quantum fluctuations, uncertainty principles, and more of them. It means that there's no notion, no sharp notion for an event, which is a particular set of measurements or quantities corresponding to a temporal spatial distance. In case this was not enough, causality is basically the same. The causal structure in space-time is basically the same up to one number as the geometry. So it means that the set of causal relations, or the statement the event A, probabilistically defined and subject to fluctuations, is causally related with the event B, with the same caveats, is itself subject to fluctuations and only probabilistically determined. And this is nothing to do with the specific formulas. And you may have a discrete spectra, you may have some notion of minimal length, as has been already discussed. So if that is the case, even if it's a consequence of just quantizing or achieving a quantum description of the gravitational field, well, a little bit, little is left of our continuum space-time picture in that context. So these are necessary criteria, agreed ingredients for any theory of quantum gravity, but how much you weight them, how much you weight the control you achieved in some of these issues, varies. And there are examples of theories that are supposed to be or constructed to be quantum versions of general relativity, and which achieve success, partial success in some of these aspects. Another point, what about observables? I mentioned the necessity to have a definition of local observables. Sometimes you hear, well, there are no local observables in quantum gravity, which, again, provided we understand what we're talking about, may be obviously true or obviously false. The obviously false aspect is the fact that I do speak regularly of here, now, and so on. So, and we do local physics. So there must be a way in which these statements appear maybe only some approximation of the full theory. But you need to know how to formulate those statements in the full theory to see if they are they acquire a sharp truth value or not. And that's the issue of having local observables defined in the full theory. They are trivially true for the following reason, that we know that classical GR is a background independent and diffeomorphism invariant theory. Now, I'm sorry for my friend, I think it was Petra, who was complaining about the notion of background independence. You can make it muddy, you can make it confusing, but the statement is very simple. Is general relativity a background independent theory, and in what sense? Well, it is in the following sense, that it is diffeomorphism invariant, okay? And it does not involve any absolute structure that encodes geometric properties. So spatial, temporal, local properties. In that sense, is a background independent theory. The geometry, anything that will define diffeomorphism invariant space-time observables will also make them dynamical in the theory. The statement about the classical theory, and there's no argument, I'm sorry. There are other types of background structures in classical GR, the global topology, the signature, the dimension, and so on, but this is not what people refer to when they say that GR is a background independent theory. What does that imply? If you take it seriously, it implies that you only have to work with different variant observables, because that's the signature of the theory, of the classical theory. And points, directions, atlases, coordinate systems are all unphysical. If you attribute them a physical meaning, it can only be in some approximation or in some more metaphorical sense. So when you talk about space-time in general relativity, well, space-time is not the manifold. The events are not the manifold points. the time is not some particular time-like direction, and so for space. Oh. So the field themselves, if you interpret them as the value of the metric field at a given point in the manifold, and the same for the electromagnetic field, are not physical for the same reason. They are not different variant quantities, and they don't satisfy the symmetries. So if you want to add in classical GR a physical notion of event, space, time, and so on, you have to define such notions in terms of observables, which are different variant and constructed out of these unphysical objects, which are the fields defined on the manifold, because they are anyway your dynamical variables. This is the issue of constructing local observables in classical GR. At the quantum level, it becomes the statement that the theory will be is a fully constrained theory, and it doesn't feature any pre-selected notion of time, space, and so on. And so there is the problem of time in quantum gravity that is already there in the classical field. There are additional issues related to this in the quantum version, but the root of the problems are all there in the classical field. So again, the problem is not even that you want to construct different variant functions of the fields, because that you can do it. The full integral of the volume element, even weighted by some other quantity, over the whole differentiable manifold, is a different variant quantity, but it's not a local one. It will not correspond to anything you actually measure. Even in some approximation, we don't measure the space-time volume of the universe from Big Bang to whatever else. So this is the problem of constructing local different variant observables. We have, in some approaches, it is more developed, in others less, but a general strategy is to construct such observables by establishing and defining and computing relations between different fields, so that the dependence of the space-time manifold basically drops, and you're left with a different variant quantity. And without giving you more details, to some extent, the task is to realize that in physical terms, what you call time is the reading of a clock. What you call space is the reading of a bunch of rods. And you may use some of the fields in your theory as your physical reference frame, and the dynamics and properties of the other fields have to be expressed in terms of your chosen physical frame. This is a strategy. Of course, there are a number of issues with reproducing standard usage of general relativity, but also how to actually compute these observables. But the general logic, I hope, is quite clear. And in full GR, we are not able to do it. GR is not type of theory that, unless you introduce very special and sort of unphysical type of fields, or you go to a very special approximation, does not allow to be deparametrized. That doesn't allow to be recast entirely in a different variant language, in terms of different variant quantities only. And at the quantum level, it's even worse, because your physical frame will be a quantum system. So it will be itself subject to quantum fluctuations, uncertainty, entanglement, and all of that. So this is the issue of constructing local quantum gravity observables. What if the fundamental entities are not themselves spatio-temporal? Well, then you have an additional set of issues, because everything that I said before assumed that you have in your hands the metric field, maybe quantum, for the quantum states, or the metric field, the same for matter, and so on. But if those themselves are emergent notions, well, you must have solved additional issues before getting to that point. And just to make clear, normally we see quantum gravity as the problem of combining GR, and the gravitational theory, so Newton's constant with the relativistic aspects, so the velocity of light, and the quantum properties that come from quantum mechanics. So we live in the so-called Bronstein cube. So we have some basic frameworks, we put them together, and that's, by the way, how the notion of the Planck length as the relevant scale for quantum gravity effects comes in. But this basically assumes that gravity and spacetimes are fundamental notions. Otherwise, you would have to replace that with what I call the Bronstein hypercube. There is one additional direction. It has to do with the direction in which whatever are the fundamental degrees of freedom that are not directly space-time fields, including the metric, somehow interact and you study the collective behavior, and you take into account more and more of them. Different approaches may have different suggestions for what the starting point is, what are the fundamental degrees of freedom, different tools for taking this limit in the n number of degrees of freedom direction. And this is the continuum limit problem. So there is a new direction of our understanding of the world, which has to be considered and evaluated. When you look at the specific quantum gravity formulas, you have to ask how we deal with this extra issue. And again, there are a number of examples that I could put forward of formalism in which this issue has been tackled, partially or completely solved, and so on. Matrix models for two-dimensional gravity is the simplest example. I should have cited a paper by almost 20 years ago by Nathan Seiberg, in which he was listing a number of examples of space-time emergence. Matrix models is the prototypical one because it's also very simple. And people develop a higher dimensional generalization of that, and there are results in which, at least in some corner of the theory, for some subset of observables, you can show indeed that there is a good space-time interpretation coming up. And group field theories that I work on are literally, I mean, you can see them as Jane mentioned, as a reformulation of a way of formulating the quantum gravity, and that's certainly a good way of looking at them. But you can simply see them as a higher dimensional generalization of matrix models, with the additional degrees of freedom needed because space-time physics in higher dimensions is much more rich and interesting, luckily, than the two-dimensional case. This is the other issue. I mentioned that this is the other ingredient. And for example, this is how to recover that is clearest, as far as I can tell, in the string theory case, as well as in the asymptotic safety context. To some extent, because the language is already much closer to this type one, despite many more ingredients in the string theory case, or the non-perturbative treatment in the asymptotic safety. But the language makes it a little bit easier to connect to this, to achieve this type of condition, this type of result. Okay, so this is again this just for further summary. Well, so again, some approaches succeed or obtain more progress, and then it's a bit difficult to judge exactly how much in some tasks, some in others, and so on. And this is a nice picture. So these were the necessary ingredients that we all agree any theory of quantum should have. I mean, you can formulate them a little bit differently, and the specific way depends on the approach, but I think we all agree, despite the fights and problems with communication across different approaches. We agree about those ingredients. Then there are a number of extra options. Additional things that may well be there in quantum gravity. It would be nice to have, that we may expect to have, but they're not part of the sort of logical necessity. So, and again, I mentioned many of them. You may just want new symmetries or new particles because it gives you more chances for experimental testability or new interesting phenomena. You may want manifest background independence, which is a different thing. I mean, background independence, at least as in GR, well, is the sort of the bare minimum. At some point, in the classical theory that you started from as the type of feature, well, we should have it in the full theory. Again, it's not really a logical necessity, even that you could imagine that something like the symmetry of GR emerges, but I don't know any example in which that happens. But you may say, no, I really strongly value the fact that the particular approach is manifestly background independent. It's not formulated in terms of any auxiliary structure that later I will have to prove or drops out of any quantity. We may want to preserve a number of features of the usual quantum field theory. It's not a logical necessity that we have to preserve them, but it could be a criterion for preferring one approach over another, including unitarity. And there are a number of background structures in classical GR that we have no compelling reason to expect to be dynamical in the full theory, but may well be. The space-time topology doesn't have to be dynamical, but it may well be dynamical and subject to quantum fluctuations. The space-time dimension, the space-time signature, the difference between Euclidean, locally Minkowskian space-time properties. And moreover, maybe you want some that the theory gave you also a generalization of standard quantum mechanics. Maybe you even ask that it solves at least some of the open issues in the foundations of quantum mechanics. The measurement problem, the issue with local realism, and it's not unreasonable to hope or even to expect that. That is just not a necessity for a definition of the theory. A theory that doesn't do any of that, but does all of the previous things, for me is a complete theory of quantum gravity. Then we do experiments and check that there's nothing missing that in the theory. I put unifications here, and just because I distinguish between having a unified framework, which is indeed a logical necessity. You want a unified framework for all matter we know, all fields we know, the gravitational field, space-time, and so on. And having a unified substance, meaning there is some single entity that in different regimes looks like the gravitational field, some electromagnetic field, some other interaction, and so on. It's great if we realize it, and approaches that they do. I know all the string theory. It's clearly a big achievement, and it's a big plus. And it implies the first, but again, it's not a logical necessity. So when you evaluate, when you try to judge, why is it that these people are not, don't do a particular, don't follow a particular research direction? Well, what's often is because some of this for them are just not particularly relevant. They're not among their main motivation. And I can mention more that different approaches fare a little bit better or a little bit worse, my judgment, on these various approaches or these different ingredients. We know examples of approaches to quantum gravity where topology is dynamical, in the sense that you can really sum over topologies, not just the topology somehow is, you see one topology in one case and different topology in another. I mean, an explicit sum over topologies. Again, matrix models is the simplest, and tensor models is another context in which we have them under control. And the same control, we have it in some examples of group field theories. Space-time dimension. You can have a dynamical space-time dimension in different understandings, in different senses. But we have examples in which, for example, at macroscopic scales, the dimension appears to be 4, and at the microscopic scales, it rounds to 2. And the way you do that is to compute observables and check what effective dimension they correspond to. And by the way, we have examples of dynamical signature and a number of other ingredients. Unification, I already mentioned, we have an example. And what about, and I didn't mention, okay, I didn't discuss more the desideratum of having the wish of having a fundamentally discrete theory. In some cases, is a tool in some approaches, but we don't care about having that discreteness at the fundamental level. In others, is a requirement. The theory has to give you some fundamental discreteness. What about the physical puzzles? I mean, I mentioned some of them. Are they solved by quantum gravity approaches? People earlier have discussed black hole entropy. Of course, what we mostly care about are black holes in the sky, but if you have a more, how to say, even if you solve the problem with toy models, at least it is an indication you may have understood something about the realistic case. And instead, I just mentioned the fact that the same is true. We have examples of dark energy or cosmological constant being a quantum gravity effect. I'm not judging these results, but just to say that there are examples which at least shows in what way quantum gravity could explain features at large scales, at late times, and so on. And well, and I'm not going to judge, but because I worked on some of that, and then my judgment is more or less positive, but I can also tell you everything we are missing in this particular direction as well, for full disclosure and honesty. But again, we have examples. So once more, also from this point of view, this desiderata, which are not logical necessities, there is a variety in the landscape, and some approaches fare better or worse, and have done more or less. So it's worth emphasizing that beside the issue of empirical guidance that is missing in quantum gravity, all of what I said earlier should show that we have an additional task, an additional difficulty in quantum gravity, which is that is the task itself, which is ambiguous. So there are some ingredients, but what will count for, okay, I've done it, I have the theory. It's very complex. There are many issues there. Okay, so this is the summary. So a first way of doing a non-empirical theory assessment is in terms of theoretical success. You look at specific formulas in light of the list of requirements that are shown, and you say, okay, these are the results with respect to issue 1 in this approach, and these are the results in terms of issue 2, and then you decide, you judge if the achievements are enough to feel partially satisfied, to assess positively your theory or not. And you can try to do, of course, comparison between different formulas. Again, it's not just you can do it, we do it all the time. The point is just, okay, do we realize exactly how complex is the actual task and what are the many aspects there? So this assessment is interesting and useful and necessary, but it has to be done with a lot of caution, because we are not only fallible people, but extremely gullible people, including the scientists. Sometimes the scientists even more. Now, this is a joyful way of putting a typical cognitive bias. But of course, this is a parody, but these are the sort of problems we may have as scientists in trying to put our prejudice, our biases in assessing theories, including our own, in fact, starting from our own. Okay, so let me take a closer look. We have 10 minutes. So yes, I have 10 minutes.
10 minutes is fine. Just have a translation.
So now I just want to conclude by discussing a little bit more the general issue of non-empirical theory assessment. In general, and in light of what I said about the quantum gravity problem. The problems. So I think that the first two parts we all agree. that it's a necessary component of what we do as scientists, and is also subordinate in scope and strength to empirical theory assessment. Okay, I think it's useful to separate the descriptive aspect. So when I study what are good criteria for theory assessment, I just describe what people do and how they reason and what are the ways in which one can perform non-empirical theory assessment. From a normative aspect, which is what people should do, what would be useful to do, is two different things. They're related. And that's the fourth point. They are related because I don't believe also in the distinction between theory construction and theory assessment or justification. The two things go together. And so normally one emphasizes this aspect to say, look, non-empirical theory assessment is actually part of assessment. It's not just the heuristics of theory construction. And that's agreed. But for the same reason, you have to consider that non-empirical theory assessment feeds back on theory construction. And I will just state that if you focus on the normative aspect, for me, a criterion for judging if a particular non-empirical theory assessment criterion is a useful one is exactly if it fosters progress, if it helps constructing better theories. Okay, and supposed to be another slide. Okay, yes, they don't do that. So I focus just on Richard's favorite assessment criterion, which again, we use it all the time. What I'm going to complain about, so it will be 5 minutes of complaint, and then we can, I hope we will discuss, is that we use it all the time. And the way we normally use it is like there's no real alternative to my favorite quantum gravity formalism. And then you put which one is your favorite one, and each one of us has his favorite one, and there's no alternative to that in the sense that I do believe that's the right one and the one that is worth pursuing. So this often is made as a purely political statement, and I'm not just referring to one or the other sub-community. It works for every sub-community in the same way in which people use it. They use it this way, unfortunately. And I only focus a bit more on what I think are the serious methodological aspects. So I start with the descriptive one. A cautious scientist who wants to be careful will phrase it in the form of there exists the best among alternatives that I have identified. It will never be really there's no alternative to some, because we know as practicing scientists that alternatives exist, or I can easily make up an alternative. Just that it may not be convincing, it's not fully formed. But it's a different type of statement anyway. So in fact, I would claim that it's simply never true that there is only a single theory or model or hypothesis that is able to explain, as a matter of principle, a given phenomenon. If you intend that the community of scientists was only able to come up with any such a theory, even after a lot of struggles and a lot of time and so on, I think I can find a counterexample to every example. But the point is that certainly it's true, not true in quantum gravity, given what I said earlier. Now I'm focusing, even if I take it in a milder form. Now, there is the best, is clearly identifiable what is the best of a number of alternatives that people have come up with for a given problem. Even in this milder form, I think we should ask, and it's an interesting research question, how is it that people reach a particular consensus around a particular alternative as the best one? Okay, normally, empirical test. If you talk to a condensed matter theorist, he will agree that, yes, of course, do non-empirical theory assessment, but yes, we normally give me your model, I check, and if it doesn't work, it doesn't work. Okay, that's not the case in quantum gravity. Very often, and it should be clear in light of the multifaceted set of quantum gravity problems I mentioned, we do it by definition. What the statement, there is one bad alternative to something, for a given problem, is actually hiding a move by definition, an assessment by definition. Meaning, we exclude all alternatives to a given one because they do not fit a set of previously chosen desiderata. And by the way, often in practice, it means that they don't follow from some established way of addressing physical problems. So, and this desiderata enter the definition of the problem. And the issue here is that, especially in the quantum gravity context, which features you decide to require. Which parts of an existing paradigm, like, I don't know, the paradigm of quantum field theory, effective field theory, or some very successful one, which ones are you fine dropping? And which ones would you resist dropping? What about mathematical ingredients that you believe should be there? And if they're not there, this for you will be a reason to discard a particular formula. I mentioned background independence. There may be physical requirements that have to be there. You decided they have to be there. What about the level of mathematical rigor? Would you say, okay, yeah, there are these alternatives, but these are so vaguely defined, they're not yet at the level of rigor of mathematical physics, so I don't even count them as an alternative to a given one, which is much more rigorously set and formulated. And I can make a number of additional criteria that you could use there, but amount to a definition of the problem. Or sometimes you actually compare alternatives. We do that again all the time. But this comparison is also not straightforward. It's absolutely not clear-cut. And that's a virtue. That's good. It shouldn't be. So consider simply the question, do you include in the comparison alternatives which are severely underdeveloped? Theories are really reserved problems. We don't really compare, the set of statements and logical statements in mathematical formulation, and we call that the theory. Our theories are not there. We're doing physics. So, do you compare? You compare a theory which is not fully mathematically developed, but to a large extent, with one which is underdeveloped. And if you do, okay, how do you ensure any sort of fairness, intellectual fairness in the comparison? And again, the point is that what matters is also the comparative dynamics of theories. Theories are not fully formed. They're not set of logical statements. It's really comparison of research programs, research directions, and comparison of progress. I could, of course, say, no, the severely underdeveloped ones, no, I put some threshold. Because otherwise, the comparison will not be fair. In order to have some level of fairness, I put some threshold. Okay, this doesn't really solve the issue because the threshold is ambiguous. And it's ambiguous qualitatively, what are your criteria, but then, of course, even more quantitatively. How do you measure how much developed is a given theory? When do you want a mathematical proof of a given result, or is enough to have a lot of evidence in the sense of theoretical physics? Now, again, we do this comparison. It's not that we don't do them. The problem here is to elevate this type of comparison to a sort of logical statement, even if probabilistic, about the viability of a theory based on this type of assessment, in my view. Doesn't mean that you cannot formalize it. I'm saying that in practice, it has a very limited value. You can also put together only compare theories which are similarly fully developed, but then it's the special case of the previous threshold. You put the threshold very high, and you may be left with no alternative to a given framework, but then it's exactly the problem I mentioned earlier. You can exclude theories either by definition or by raising the threshold of comparison, of development on some specific criteria, because maybe you don't do it in all of them. You say, okay, I'm fine if they haven't shown UV finiteness, which could be a criterion, but I'm absolutely not going to accept a theory which is not proven that you can recover the black hole entropy at the level of mathematical physics. I don't know, for the Schwarzschild black hole. Okay, so at the end of the day, this last choice, which seems reasonable, is the fairest one, ends up being, to a large extent, an elimination by definition. So, to summarize, I mean, the main problem with this type of argument, taken as a sort of logical assessment criterion, not just as a, part of your work, you have to make assessments, reject papers, give grants, and so on. You have to add your criteria. Well, the main problem is the following: that if I want to summarize, is that even if the premise of the argument for an increased viability or correctness of a theory following from the non-existence of alternatives was true, even if the argument was true and the premise was accepted, the premise itself is the result of non-empirical theory assessment. And it doesn't mean that the argument then is wrong, but the interesting part then is which non-empirical theory assessment criteria led to the establishment of the premise. So if you're interested in methodology, are those other preliminary criteria that should be the subject of your interest? This argument in itself, okay, it may be an intermediate step in a set of arguments, but okay, for me, it's not particularly interesting. Okay, and of course I can say more about that. And focusing on the argument per se, on the no alternative statement, distracts from actually studying and understanding better the previous arguments, the preliminary assessment. Then, okay, it also, this type of argument forgets all sorts of other factors, psychological, sociological, historical, and so on, but okay, this is a different story. And to conclude on the normative aspect, well, there is a normative aspect, whether we want it or not. The moment we give an assessment of theories, that influences which theories we decide to construct, which theories we decide to invest our time on, and so on. So it influences what you're supposed to be doing. And in fact, this type of no alternative standpoint becomes basically a statement of fact about the consensus reached in a given community. And so either you are assuming perfect group rationality, or you're just stating a sociological observation. And so I'm not sure exactly how much you're learning. And assuming perfect group rationality is a big assumption. Moreover, this way of assessing theories based on this type of no-alternative reasoning feeds back on the consensus reinforcing it. Now, to make a longer story short, it does exactly what a sound methodology shouldn't do from a normative perspective. We have learned that we have to try to falsify theory. Now, of course, falsifications and proper methodology is superficial in many ways. It's just a general scheme. But one lesson was you shouldn't try to verify and confirm your theories. You should try to falsify. You should try to increase and maintain skepticism about your theories. That's what the methodologies should do. Okay, so how do you react then to a situation in which you only have non-empirical criteria? There may or may not be more or less consensus about the specific alternatives. Well, I would claim that the only progressive strategy is to double the efforts to develop your theory, the favorite one, to the point in which it can be empirically tested. That's the main point. But also to develop actively the alternatives further so that they overcome the current difficulties and offer a stronger challenge to the failure theory. And if you can, try to produce even more alternatives to the established or more consensual existing ones, even if it's more than one. Try to come up with more. So you should base non-empirical theory assessment on proliferation. Now, the reasons for that is you can give two sets of arguments. So there are general ones, failure in proliferation, that you can take from John Mill, Popper, Feyerabend, and a number of other people. Normally, they were thinking about empirical assessment, but I think the same arguments hold even more for non-empirical theory assessment. And then specifically, in the case of quantum gravity, well, if proliferation is needed according to the classical arguments in times of crisis, when you have to change paradigm, where you are a bit unsure about what is the right framework, well, quantum gravity fits the bill. There are so many and so radical aspects of the quantum gravity program that the exploration of possible partial solutions, partial results, and new intuitions, and so on should be even broader than normal, not less. And the type of revision of the foundations, again, of accepted principles is clearly going to be so strong that we should rely even less on the accepted principles, and that calls for even more proliferation of alternatives. And here I just offer 4 criteria, and that's the last slide. What could be useful non-empirical theory assessment criteria or methodological guidelines or suggestions for progress in the quantum gravity landscape? Okay, produce even more alternatives if you can, and develop alternatives which are underdeveloped even more. I mean, they can become a priority for methodological reasons. But also, well, a theory that combines several mathematical structures or ideas found in other theories, in other approaches, in other programs, has an increased viability. A theory that once you have proliferated, I mean, if you find that you proliferated even more, and you find that there is one of them that actually seems to be a combination of several of the others, it includes several of the insights of mathematical structures, well, that's a plus. But you need proliferation in order to apply this type of criteria. A theory that connects, again, naturally and generically to some class of phenomenological models among many alternatives, then it has a good chance of being empirically testable in the future. So that's an additional plus. A theory that, given many other approaches, can explain why they are likely to fail. Not just, prey on their current failures, but explain why they are failing. And then you can just go to your colleague and say, look, I have this result. Under such premises, which are, by the way, shared also by you, it's clear that you're going to fail on this problem. I can show you within this other formula. Well, that's a plus. A theory that can do that is a plus. Or a theory that solves open issues in other approaches. In order to apply this type of criteria, you need all the other approaches to increase the viability of your theory. Thank you.